me without it? Yeah.
Yeah.
In the back, can you hear me? Yes. Okay, so I'd rather prefer not to use it if you like it. First of all, welcome everyone. Thank you for coming. Welcome to this presentation of my honors project for this year, which was the synthesis of lanthanide-based mesoorganic frameworks using 1245-benzene tetracarboxylic acid as my ligand, and this is for possible applications as chemical sensors. My supervisor was Professor Larry Watkins, and my co-supervisor was Dr. Kevin. Now, before we carry on too far, I need to explain what a mesoorganic framework is. Mesoorganic frameworks are supermolecular structures which are metal sensors or metal oxide sensors, which are joined with organic ligands in a coordination network which can be porous in nature. Now, this porosity is what is of importance in these particular structures. Porosity allows for the inclusion of foreign guest molecules, such as gases or small molecules in liquid form, and these are included inside the molecule. And the presence of the organic liquor differentiates them from zeolites. Zeolites are naturally occurring aluminosilicate materials which have been used for the past century possibly as compounds which can include molecules like the mesoorganic frameworks. But these occur naturally, as I say, and they've been used in catalysis and other applications. And we are now trying to synthesize these mesoorganic frameworks to form similar structures to the zeolites. Now, this is a typical moth image. This over here, you can see it clearly, is a rigid framework with included molecules. This is a combination of different metal sensors, all linked with some sort of ligand in this particular case. And then this over here is just a unit cell, which with this yellow volume here being with the space in which the particular molecule can include itself into in the molecule. Now, there are different applications of mesoorganic frameworks. We can use them as chemical sensors, and this will be the main focus of my project. They can be used as drug delivery agents in the human body, whereby they include the molecule and then release it in specific active sites in the body. They can be used and have been used in gas storage devices, especially for gases such as hydrogen, which have shown a very difficult molecule to transport around via the traditional gas lines. And we also have the use of optoelectronic devices, catalysis, especially in the form of heterogeneous catalysis, and there are a variety of other applications which are not going into at this point. Again, I'll be focusing on the application of MOS as chemical sensors. Now, just to look at my ligand of interest, benzene tetracarboxylic acid has multiple coordination sites, and this is dependent on the amount of deprotonation which occurs. As you can see, the carboxylic groups there are 4 of them, as the name suggests, and if they are all deprotonated, this affords different coordination structures to be formed with the metal or metal oxide. Another important thing is that C, as I call it, can act as an H1 donor or acceptor, which is very important in terms of coordination chemistry. And it also allows for tunable pore size, again, due to a degree of deprotonation. And this is also quite vital, and we'll look into this just now. Also, just to mention the metals which I'm using, I'm using the lanthanide metals. Now, these are an interesting group of metals as they exhibit interesting luminescence properties due to the presence of the 4 F orbitals. And these metals exist primarily as in the 3+ oxidation states. Now, this allows them to form high coordination structures with the 4 F orbitals and the ligand of interest, and this is why this particular metal was chosen. I, in my study, focused on gadolinium, dysprosium, erbium, and ytterbium. Now, just to mention why we're looking at the use of MOS as chemical sensors, volatile organic compounds are a health risk in high concentrations. And we need to be able to accurately detect their presence, and then once we know of their presence, quantify how much of them there are. Now, we need reliable methods of detecting these VOCs, and MOS are good candidates for this particular detection, as we can manipulate their properties in order to make them good sensors, especially lanthanide fluorescence properties. Now the aims of my study, as it is an honors project, we have too much time, was to simplify the MOF, which has potential for guest inclusion. Second part was to characterize the MOFs once fully synthesized. And then the third part of my project was to determine the fluorescence activity of this particular MOF. Now, before we could actually go into the project, we have to first find structures which fit the description of what we're trying to make. So in order to find structures, I searched in the Cambridge Structural Database, which is an international database of crystallographic data and crystals and MOFs and the like, and proteins and whatnot. And then my criteria for structure was to find a structure with medium to large pore size, which would be able to accommodate water, methanol, or whatnot. But for my study, I just looked at water as being included in the molecule. Only B4C and at least one lanthanide metal had to be present in the structure of interest, and no other organic ligands were supposed to be there. So no bipi, no anything else except B4C. Of the thousands of structures on this database, I only found 3 which were suitable for my study, and of those 3, only 2 were suitable for this year because the other one, synthesis takes up to a month, up to 2 months, and I don't have that kind of, unfortunately, do not have that kind of time. Alright, so just looking at the different synthesis techniques used, we used hydrothermal, which was the use of an autoclave. For this particular method of synthesis, we tried it 4 times, all of them failed. This was due to the fact that the B4C was overheating and burning due to some mechanical failure on the instrument. Therefore, all my solvents, which was water, evaporated, and thus nothing was formed, unfortunately. The second synthesis method used was the sol gel, and this is an ongoing process, unfortunately, and sol gel can take many months up to years to form any useful product. And as you can see, this is an image of my sol gel reaction. This was a solution of B4C, and my metal was included in the gel before the gel was gelated. Then the third synthesis method was ambient reflux. Now, this provided the best results for my project, and for the rest of the project, I'll be focusing on the products obtained from this particular method. Now, this table is just to quantify the different products synthesized in my project. These 3 literally can be disregarded as they were just products, the residue obtained from autoclave after the stuff had burned. We tried it for the 5th time, but unfortunately due to mechanical failure, the pressure gauge actually burst. We had to abort that 5th trial of the autoclave synthesis. We then tried to synthesize this sodium gadolinium base to make some organic framework. We did it twice using ambient reflux, and we got 2 different yields. This was a particular method, and this method was adapted from the method used to synthesize these 3 MOFs over here. Now, these last 3 MOFs were synthesized using proper ambient reflux, all at the same time, roughly. And as you can see here, we performed the best yield over there, with the exception of the other gadolinium-based MOF. And as I say, I'll focus then lastly on these 3, and then later on in my presentation, I'll be exclusively focusing on my gadolinium MOF, as that did give me the best results. Now, these are the different characterization methods used in my project. The first one was to determine the amount of the functionalities present in my MOF. And for that, I used the infrared and Raman spectroscopy. X-ray part of the fraction of to try to determine the crystallographic data of the MOF. Following that, thermogravimetric analysis and differential scanning calorimetry was used to determine the energies associated with the losses of water. UV-vis was then used in PE thanks to Dr. Austin. Gas sorption, these results are still pending, unfortunately, but I will mention them briefly. And then the last thing was to characterize the fluorescence activity of my MOFs. Rehydration studies. Now, rehydration studies are important in MOFs because these MOFs need to be reusable. We need to be able to uptake water and then get rid of it and then take it up again. Now, in order to determine the properties of the rehydration properties of the moth, each sample from those products that I've shown were heated to 250 degrees in the thermographic analysis oven, and they were kept there for 5 minutes just to ensure adequate use of water. They were then placed in a desiccator saturated with water vapor for 7 days to allow the re-inclusion of the water into the structure. And then they were heated again in the TG until decomposition had been achieved, and this was roughly at around 600 to 650 degrees. And then we compared this rehydration decomposition to the original decomposition, which was done before we did the rehydration studies. Now narrowing it down, now that I've mentioned what techniques were used, what I've done to synthesize, I'll be focusing on the erbium moths because of time constraints, and then I'll take you through what's happened. And you can apply the same procedures to every single other moth which I need to construct. Now, looking at the erbium moths, we can see that there are two products there. Now, let me explain the situation. Unfortunately, we had ambient reflux. We extracted this in the first filtration, and then we took that filtrate from that first filtration, added a bit more B4C solution, and this afforded the formation of more erbium moth. Now, because we did not know if these two compounds were isostructural, we decided to treat them separately until we could affirm if they were isostructural. And as you can see, we have 12 waters coordinated there and 12.75 waters coordinated there. These values were worked out from the microanalysis, and I'll delve with that a bit later as well. Now, this is just looking at the second erbium moth, which was extracted from the filtrate. This is just to show the presence of water, and then the carbonyl piece over there is a couple of overtones, and then the fingerprint region. This is the IR, and then this is the Raman spectroscopy, and it pretty much confirms the presence of the cyclonality mentioned above. This is just a closer look. As you can see, we did 3 IRs, one for the original compound, one for the dehydrated compound, and then one for the rehydrated compound. Now, this was done for us to be able to see what kind of structures were afforded at each stage. As you can see, the first one, there is water presence at that region over there. You can see our carbonyl stretch and asymmetric stretches and bend over there. And then we can see the fingerprint region in that last point of the way. After dehydration, we can see that the water has been mostly completely removed, and we can see that there is a slight change in the appearance of the carbonyl peaks. This can be attributed to the slight structural change upon dehydration, and as you can see also the disappearance or the loss of resolution of the peaks in this IR region over there, the fingerprint region. And then upon rehydration, again, you see that the water looks similar as to what it was before. This is quite important, and it's quite exciting to see. Now, just looking at the TBA data on the thermograph, you can see from the original spectrum, which is heated all the way up until 650 degrees, we have specific stages where lots of water is seen. Lots of water, according to literature, to afford that completely anhydrous form of the moth was, you have to heat the moth to 350 degrees. Now, you can see that the rehydrates moth pretty much emulates the thermograph of the original structure, which is pretty exciting as well. And this is why I say that the erbium moth afforded me with the product, as this was the best thermograph which was seen. And this data just shows from the two thermographs the water loss experienced up to 350 degrees. As you can see, in the first moth, or the first part of the moth, which is the original moth, you see that we use 14 waters, and in the second moth we use 15 waters. Now, I assume that we can have an educated guess and say that this and this are pretty much equivalent, just the fact that I used the same molecular mass for the rehydrated moth as I did for the original moth, because we did not have enough sample to be sent through to microanalysis to determine the actual molecular mass or estimates the empirical volume mass of the rehydrated spectrum, of the rehydrated block. So you can say that these two are pretty much good, very good agreements. Okay, so moving on to the DSC, which is the differential static delivery. This was done up to 250 degrees, but I just showed up to 180 degrees. We can see here that this is an endothermic peak showing the loss of water. We can see that the area underneath there is equivalent to a specific amount of energy, and it's just to show that there was a specific water loss stage at that point. And then this data just characterizes that particular peak to show that at that stage we lost approximately 8.8 water, and that corresponded to a mass loss of roughly 9.68. And this was in temperature range of 82 to 166 degrees. Now looking at the XRD patterns, the X-ray diffractometry, we can see this is the original spectrum over here. It's quite messy, unfortunately. And due to the fact that it was so messy, we decided not to index the planes and find the crystallographic data. This would take too long, as then we would need to have constructed a single crystal for a single crystal XRD. Upon dehydration, you can see we have a huge loss of information over here. So this is probably due to the fact that most of the waters have been lost. And then upon rehydration, you see that we partially reobtain some of the data seen in the original photo. And we can see that there, this is still pretty much constant over there. So this peak over here at 4, or not 4, at 15, is slightly more intense in the rehydrates compared to the original spectrum. But then one thing which was of great interest to us was that upon complete thermal decomposition or thermal heating to the oxide form, we obtained this very clean image over here. Now this image matches perfectly with literature, so we can confirm that it actually did produce erbium oxide. And this image was taken from Dr. Database, which was used as a reference. Now just to move on to the solid state UV-vis, I decided not to include the intensities because those are irrelevant due to the fact that this is a solid state study. Now you can see that I've now compared erbium 2 to erbium 1, erbium product 2 and erbium product 1. As you can see from the peak intensities and the peak positions, these structures are pretty much isostructured. So for the rest of the talk, we can just bunch them together and say that these compounds are isostructural. This is the UV region, the visible region, and the IR region. And it was quite great to see that we had quite a bit of absorbance in the visible region, which is of great importance whereby we wish to observe fluorescence in the visible region for easy detection. Okay. Fluorescence studies for this one structure. Sorry for the very junky job over there. But as you can see, this is overlaying the UV spectrum. In the visible region, we see that we have, looking at the 200 nanometer excited fluorescence, we see that we have two peaks of great interest over there. And we can see that these peaks correspond roughly with these absorbance peaks over here. And that's fantastic because it shows that those species which absorb in the visible also fluoresce in the visible. And that shows that this block has great potential to be used as a sensor in the visible region for chemical absorption, chemical uptake. Just to conclude from the presentation, we can confirm the rehydration ability of lanthanide-based emitted organic frameworks based on our TG data, DSC data, and just from concluding from everything. And from studying the model to fully characterize these emitted organic frameworks, we have also shown the potential for fluorescence behavior in at least one compound. Now, just a brief mention of the fluorescence studies. The fluorescence studies were done in the solid state, well, because we use MOFs in the solid state. But unfortunately, we only have instrumentation for solution state fluorescence studies. So it's another future work, as I'll show you now, is that we can actually potentially collaborate with someone who might have solid state fluorescence capability to fully characterize these further, so that we can actually prove that these blocks are viable in the future. We also need to investigate the use of different ligands, because the use of E4C in itself is great, but we also need to show what kind of properties are afforded by the use of other ligands. We also need to investigate resolvation using other solvents such as methanol, DMF, DMSO, and whatnot, in order to show what kind of restorability of structure we can receive from the studies. Investigate fluorescence of desolvated MOF, which compares to resolvated MOF. And this is very important because sometimes we need to be able to investigate what would happen if a MOF was desolvated. Would it fluoresce, would it not fluoresce? And if we need to determine whether the included molecule in the MOF is itself adding to the fluorescence properties or detracting from it, thus quenching the fluorescence molecules, the fluorescence of the MOF. And that's quite an important study to be done. And then also, as I mentioned earlier, we need to determine the reusability of these structures. We cannot afford to use only one MOF. We cannot only afford to use the MOF once. We need to be able to use it again and again and again in order for industrial applicability to be ensured. And this is something that can be done as a master's project and done in the future. All that is definitely important to acknowledge these people. I'd like to acknowledge Mark Mkhize, creator and author of All Knowledge, Prof. Watkins and Dr. Locke, my supervisors, the GST, MINSEC, NIC for the use of their equipment, and the rest of the people here. Just a special mention to Dr. Eric Costin and Mr. Hank Stellenkamp of NMU for their assistance with their UV-Vis. And yeah, thank you very much for your attention.
Thank you very much to Mr. Mkhize. Let me take this opportunity and invite questions. We're going to take 3 questions at the next, colleagues. Thank you. Yes, sir.
Nice talk, colleague. My question is on the did it have to take the same amount of water that it actually lost when you did your studies?
Not all of the stuff is good. I only focus on the ambient MOF because it showed that that gave the most restorability. So it was with a standard error of 1 to 2 waters, that was the error on the ambient MOF. But some of the structures had lost like 10 and only took up about 6. So those MOFs were then disregarded as potential sensors.
So I can attribute that to?
We can probably attribute that to structural collapse, because sometimes we might have the metal not coordinating properly with the ligand. So upon dehydration, there's some sort of structural collapse, and then upon intake of water, it doesn't actually get back to the original structure. So what's done is actually include itself fully in the deposit.
Thank you.
Yes, sir.
Mr. Mkhize, I assume you presume this metal organic frameworks as being lanthanide based or compounds. Now the question is, you have heard of organometallics before?
Yes.
Which are coordination compounds. So the question is there any difference between these metal organic frameworks and coordination compounds? If there is, then what is it?
Okay, so the major distinguishing factor between natural or just normal organometallics and these ones is the presence of that core, which I was talking about. The fact that it's got the porosity, which is what you can manipulate in order to fine-tune and get specific properties out of it. Normal organometallics can be used, as you say, as just products of some sort. If you look at the porphyrin structures and thiocyanates and things like that, those are organometallic. Whereby this is organometallic in itself, but it's a specialized sector of organometallic.
Like porosity?
Yes.
So,
Thank you. Last question. I saw a hand somewhere there. Right. Looks like there are no further questions. Let me take this opportunity and thank you very much for your brilliant presentation.